Welcome to the Deep Dive. Today we are setting aside the dusty textbook generalizations and diving headfirst into the foundational research that really created our modern understanding of electromagnetism.
It's a great topic.
We are talking about the experimental notebooks, the published papers, and just the meticulous, rigorous thinking of Michael Faraday.
And this is so much more than just a historical review. It's an exploration of how a scientist pursues unification. I mean, Faraday was fundamentally interested in finding the deep underlying unity in things that seemed totally disparate.
Right, like chemistry and electricity.
Chemistry, electricity, magnetism, how a chemical reaction, a sudden spark, and the steady pull of a magnet could all be connected. The sources we have, they just detail his mission to establish universal laws based not on, philosophical musings, but on quantifiable, reproducible experimental data.
And that data, in turn, led him to these radical theoretical leaps.
Oh, absolutely. Most notably, the concept that magnetic force exists as physical lines of force that just pervade all of space.
And that really is the core mission of our deep dive today. We're going to trace how Faraday went from proving that the electricity you generate by, say, rubbing a cat's fur, the current from a chemical battery, and the energy you get from moving a wire near a magnet.
All seem totally different.
Totally different. And he proved they are all fundamentally interchangeable. And then he used that realization to categorize every known substance on Earth. And I mean every substance.
It's not an exaggeration. From iron to copper, from bismuth to the very oxygen in the air we breathe.
It's an entire classification of the material world, all based on magnetic response.
It is. It replaces that simple dichotomy of just magnetic versus non-magnetic
Correct.
with a complete spectrum of interaction. So yeah, we're going to unpack the details of how he proved this universal connection.
Okay, so let's start at the beginning of this unification project. He was trying to resolve what was really an identity crisis that electricity was facing in the early 19th century.
That's a good way to put it.
I mean, to the casual observer back then, an electric eel, a shock from a Leyden jar, and the steady output of a voltaic pile seemed like a completely different species of energy.
And that was the prevailing hurdle. Faraday's driving conviction, which, he had to prove to a very skeptical scientific community, was that all these types, voltaic, common, which is static electricity, magnetoelectricity, thermoelectricity, and even animal electricity.
From the eel.
From the eel, yeah. That they were all identical in nature. They weren't different forces, just different manifestations of one underlying power.
But just saying that wasn't enough.
Oh, no. He knew he needed clear, distinct, and quantifiable proofs to gain assent. He looked at the precedent set by his mentor, Sir Humphry Davy, who had decisively resolved whether voltaic electricity merely produced acid and alkali, or if it simply eliminated them from the apparatus. Faraday needed that level of experimental decisiveness.
And he found that definitive proof not just in the effect of the electricity, but in its meticulous measurement. This is what led to the development of what he called definite electrochemical action.
And this concept is it's foundational. It is the moment that electricity truly became a quantifiable force in the modern sense.
So what did he actually prove?
He proved that electrolysis, that's the chemical decomposition driven by electricity, is strictly quantitative and definite. The quantity of chemical change you get is exactly proportionate to the quantity of electricity that has passed through it.
In that phrase, quantity of electricity, that's the revolutionary part, isn't it? Before this, scientists were mostly focused on intensity. The voltage, the strength of the shock.
Exactly. Faraday was showing that the intensity didn't matter if the total charge, the actual quantity of flow, was kept constant.
So you could have a really slow current running for a long time.
Or a swift, intense jolt over a short duration. As long as the total quantity of charge delivered was identical, the amount of chemical decomposition you achieved was also identical.
Which demonstrated a fundamental universal law.
A law governing the relationship between electrical current and chemical matter. And to prove this was universal, he ran these incredibly controlled comparison experiments.
Can you walk us through one of them, just to show how it held true, regardless of the chemical context?
Certainly. One of the most powerful examples involved comparing the volume of hydrogen gas that was evolved in 3 very different chemical solutions.
Okay.
So he used dilute sulfuric acid, an ammonia sulfate solution, and a subcarbonate of potassium solution.
Very different chemical environment.
Vastly different. But the quantity of hydrogen that was produced at the negative electrode was the same in all 3 cases. That consistency, regardless of the accompanying acid or alkali, was the irrefutable evidence.
So the amount of charge The quantity was the only thing that determined the amount of chemical change.
The sole determinant.
It almost sounds like he was quantifying the flow of electric charge using the atom itself as a little measuring cup, long before anyone really understood the electron.
That is the extraordinary implication. He realized he had a universal measure, and this led him directly to his invention of the volta-electrometer.
A volta-electrometer.
Yeah, this was a device he designed specifically to measure the quantity of electricity by the chemical effect it produced. And it allowed him to establish what he called definite electrochemical equivalence.
So he's putting numbers to it all.
Hard numbers. By setting oxygen's equivalent weight at 8, assuming hydrogen is 1, he demonstrated that the same power that was responsible for electrodecomposition was the very same power responsible for ordinary chemical attractions. He had mathematically linked chemical structure to electrical quantity.
Okay, so the electrical current is one unified force, and its effect is definite and measurable. But the next big debate he tackled was, where does the battery current actually come from?
Right, and this challenged the long dominant contact theory.
Which was the idea that
The prevailing theory argued that electricity in the voltaic pile, in a battery, arose simply from the contact between two dissimilar metals. It was seen as a purely physical surface phenomenon.
But Faraday, armed with his proof of definite electrochemical action, he just refuted this completely.
Emphatically. He argued that the electricity of the voltaic pile is not dependent on the mere contact of metals. Rather, he insisted it is entirely and solely due to chemical action.
So the battery isn't some miraculous generator of force just through contact.
No.
It's just a device that channels the latent force that's being released by ongoing chemistry.
Exactly right. And he established two critical rules of proportionality for the current. The intensity of the current is proportional to the intensity of the chemical affinities at play.
How strongly the chemicals want to react.
Precisely. And the quantity of the current is proportional to the quantity of matter that has been chemically active. So if you stop the chemistry, you stop the electricity.
And to prove this, he had to show that you could generate electricity without the typical zinc and copper plates touching an acid solution. He had to use some really unusual non-metallic mediums.
Fused salts. Yeah.
Fused salts.
And that's where the rigor of his experimentation just truly shines. He demonstrated voltaic action when substances like fused niter, that's potassium nitrate, or chloride potassa or chloride of lead were interposed between copper and platinum plates.
So these are molten, non-metallic chemical compounds.
They are. And the fact that a current was produced when these substances, which were undergoing decomposition, were the intermediaries, it just completely undermined the theory that metal-to-metal contact was the necessary source. The current arose from the ongoing chemical breakdown of the fluid in between.
This level of detail then leads him to classify what bodies can even participate in this chemical electrical dance. He calls them the electrolytes.
Yes. Electrolytes are simply compounds that are decomposable by the electric current. But their functionality, it comes with a very specific, rigid condition. They are governed by the law of liquido-conduction.
Liquido-conduction.
They must be fluid, either molten or in a solution. They have to be fluid to conduct and be decomposed, and this rule was absolute.
So fused salts worked.
But solid salts did not. This is a crucial distinction about the necessity of molecular mobility for a current to be transmitted.
And that necessity is maybe best illustrated by his famous experiments showing the insulating power of ice.
Oh, it's a spectacular demonstration. It really shows the importance of phase change. Water, a very common electrolyte, becomes an extreme non-conductor when you freeze it.
So how did he test this?
He detailed using a powerfully charged battery 15 troughs, amounting to 150 pairs of plates to test it. He placed platinum electrodes separated by what he called an extreme thinness of ice.
Just a sliver.
A sliver, and no sensible electricity could be made to pass.
Imagine the conditions in a 19th century lab trying to maintain that tiny sliver of ice separating plates while you're applying immense electrical pressure.
I know.
Just to prove a point about molecular arrangement, it really speaks volumes about his dedication to isolating every single variable.
It really does. And it highlights the requirement for perfect insulation, which leads to another interesting note, actually. The materials he began using to achieve this kind of experimental purity.
Ah, he mentions gutta percha.
He does. The introduction of new materials was often the key to unlocking new experiments. Gutta percha was a relatively new material. It's derived from tree sap, and Faraday immediately recognized its value.
It was better than what they had before.
Oh, much better. He highlighted its superior qualities over older materials like shellac, noting its high insulating power combined with a much-needed flexibility and toughness.
Right, which would be essential.
For someone doing high-precision electrochemical experiments, having highly reliable, flexible insulation for wires, plugs, and supports was essential for preventing leakage and just maintaining the integrity of the measurements. The material itself became an enabler of more rigorous science.
So, if Section 1 was about proving what the electrical force was, Section 2 tackles the far more controversial question of how it exists and travels through space.
Right.
This is the radical leap from action at a distance to the concept of physical lines of force.
This is where Faraday steps definitively away from the dominant Newtonian tradition. Newton had posited that gravity, for example, acts instantaneously across vast distances.
Action at a distance.
Action at a distance, with no known medium in between. Faraday found this concept really unsatisfying for magnetic and electric forces. His core philosophical question was whether these magnetic lines of force have a physical existence in the space between the magnet and the object.
And to frame the discussion, he compared magnetic action to 3 other known forms of force transmission.
He did. He looked at gravitation, where, as we said, propagation is not supposed to exist across the distance. Then radiation, like light, where the propagating line exists independently once it's emitted, regardless of its source or where it ends up.
And the third.
And electricity, so induction, where propagation exists, but its state depends on both the source and the termination, or the conditions equivalent to them.
And he landed on a mechanism for magnetic force that was distinct from all 3 of those. And it was really rooted in his chemical background.
He hypothesized that magnetic force propagation occurs via the action of contiguous or next succeeding particles. In this view, force is not some mystical action over empty space. It's a chain reaction.
So the particles in the medium itself are part of the process.
They are the process. The particles in the medium, whether it's air or glass or even a vacuum, are thrown into a state of tension or polarity.
Like stretching a rubber band.
That's a great analogy. This state is forced upon them, and they constantly tend to return to their normal condition, just like a spring being stretched. And this unifying idea that induction and conduction both rely on this localized contiguous particle action was absolutely key.
Now that's a beautiful theory. But how do you prove the physical reality of an invisible line of force if you're trying to move beyond just sprinkling iron filings on paper?
Right.
How do you map it quantitatively?
This is where he invented the experimental methodology that secured the physical reality of the lines. He collected and measured the electricity induced in a moving wire that physically intersected the lines of magnetic force.
So you're not just looking at a compass needle twisting.
No, this was fundamentally different. The moving conductor literally quantified the number of force lines being cut as it passed through them.
So if the amount of electricity you produce is directly proportional to the number of lines you intersect, that gives you a precise mathematical measure of the force density in that region of space.
Exactly. But there was a major experimental hurdle. The induced electricity, while he said it was abundant enough in quantity, was so feeble in intensity.
So a lot of it, but very weak.
Very weak. A standard galvanometer, which used fine wire wrapped many, many times, was useless because that fine wire increased resistance and it just reduced the already low-intensity current to an immeasurable trickle.
So he had to build an entirely new type of instrument, one that was optimized for this high-quantity, low-intensity current.
He had to maximize conductivity. For his simple circuits, he just used stout copper wire, 0.2 of an inch in diameter. Thick stuff.
Right.
But for his most sensitive measurements, he constructed a galvanometer where the conducting coil was essentially solid metal. He cut it from thick copper plates and formed it into a square band, 0.2 inches thick and 24 inches long, that went around the needles.
Wow.
These modifications were crucial. They allowed him to detect effects that were 30, 40, or even 50 times greater than those he could observe with the standard fine wire instruments. It was a triumph of engineering rigor that enabled a theoretical breakthrough.
So using these new super-sensitive instruments, what did he discover about the architecture of these magnetic fields?
He confirmed several key geometric characteristics of the lines. First, they don't just stop at the surface of the magnet. They exist both within and outside the magnet.
Okay, so they go right through it.
They go right through it. Second, they are closed curves. And this is a powerful concept. The lines have to complete a continuous path, passing in one part of their course through the body of the magnet itself.
That makes the magnetic field a complete self-contained continuous circuit.
It does. And the third, and this is mathematically elegant, was his finding that the total amount of force inside the magnet at its equator is precisely equal to the total amount of force existing outside of it.
A conservation of magnetic flux.
It proved the continuity of the lines. And furthermore, he noted that when lines coalesce, like when you put parallel magnets together with their poles aligned, the quantity of force is simply summed. They add up.
And to demonstrate the nature of induction as this contiguous polarized state, he used static electricity, didn't he, to show that force lines could be curved and redirected.
Yes, to prove the medium matters. In one experiment, using an excited shellac cylinder and a brass hemisphere, he mapped the inductive force. And instead of the field lines following straight paths, which action at a distance would suggest, they were curved and distorted by the presence of the brass hemisphere.
So they were bending around it.
They were bending. He found the inductive force actually diminished and then increased again at certain points, which could only be explained if the force was transmitted through the intervening particles, which were themselves being polarized and reacting to each other. He called it a lateral tension. This visualization was a powerful precursor to modern field theory.
Okay, so after establishing how electric and magnetic forces are unified and how they travel through space, Faraday then turned the full power of his experimental apparatus onto all known materials. This is where he discovers the great magnetic division of the universe.
And this is one of the most stunning classification systems in physics. I mean, before Faraday, materials were broadly considered either magnetic, like iron, or non-magnetic, like pretty much everything else.
Right.
Faraday shattered this. He established a new universal magnetic division for all matter: paramagnetic and diamagnetic bodies.
Let's define these behaviors, because they are fundamentally different based on how they respond to those lines of force we were just talking about.
Okay, so paramagnetic bodies, which include familiar elements like iron, nickel, cobalt, and perhaps surprisingly, oxygen gas.
We'll get to that.
We will. These are materials that are weakly attracted to the magnetic poles. They align themselves parallel to the lines of magnetic force, so they move towards the regions where the field is strongest.
And diamagnetic.
Diamagnetic bodies are, well, essentially everything else, and they exhibit a weak repulsion. They tend to place themselves perpendicular or equatorially to the magnetic force. They move away from the poles, away from the strongest concentration of the force lines.
So he wasn't just finding new magnetic substances. He was finding that every substance, including gases and vapors, interacts with a magnetic field.
Yeah.
Just in one of two opposite ways.
It was a realization that magnetic action is pervasive. It's a universal characteristic of matter. And he needed precise, highly repeatable examples of this repulsion. Bismuth became his go-to material for studying diamagnetism.
Why bismuth?
It showed the effect very clearly. He used a small bar about 2 inches long and noted that when he suspended it, it freely moved to place itself equatorially, perpendicular, and was clearly repelled from the poles. This repulsion was the signature of the diamagnetic class.
Were there any common metals whose diamagnetism was particularly surprising to people at the time?
Oh, absolutely. Copper was one. It's an excellent electrical conductor, and yet it was demonstrably diamagnetic. But experimenting with copper was challenging because of the dual effects that are present.
What do you mean?
Well, when a copper object moves in a magnetic field, two things happen at once. You get the induced magnetoelectric currents we talked about earlier.
Right, the generator effect.
And you get the diamagnetic action. Faraday had to carefully design experiments that could separate those two effects to confirm copper's diamagnetic status. Even high-value materials like gold crystals, he tested them and found they were diamagnetic.
And the complexity didn't even end with the chemical composition. He found that the crystal structure itself introduced a strange directional preference.
Yes, what he called magnecrystallic action.
Magnecrystallic action.
This was a major point of nuance. It's the surprising realization that the way atoms are arranged within a crystal lattice, its internal structure, can strongly influence its magnetic behavior. Sometimes it can even override its inherent bulk magnetic property. Bismuth crystals, for instance, exhibited this specific magnecrystallic force.
And what happened if he destroyed that crystal structure?
The force just vanished. He found this magnecrystallic effect was neutralized or lost if he finally broke up the crystal into a powder. It was also lost if he composed the crystal of 3 equal plates placed at right angles to each other. This demonstrated conclusively that the effect was dependent on the macroscopic, organized crystalline arrangement. It proved that matter's internal geometry is just as crucial as its chemical nature in determining how it interacts with force lines.
Faraday did speculate a bit on the nature of the polarity in these crystals, but I understand he quickly rejected one possibility.
He did. He considered the hypothesis that molecules within the crystal might become polar without having any mutual relation to each other, acting only in relation to the distant magnet.
So they would be like tiny independent compass needles.
Kind of. This scenario would allow the crystal to align actually without any genuine attraction or repulsion. However, he deemed this very improbable.
Why?
Because he was certain that if a particle possessed polarity, it had to be subject not only to the distant magnet, but also to the polarities of its contiguous neighboring particles within the crystal structure. It reinforced his whole theory of contiguous particle action.
Okay, let's turn to what might be the most important experimental check of this entire section. The test that determined whether diamagnetism truly represented a reverse polarity.
Right.
I mean, if bismuth is repelled, doesn't that just mean it must have a magnetic polarity that's the opposite of iron?
That was the widely accepted common sense view. But Faraday's unified theory, rooted in that moving wire method, suggested something else was going on. So he performed a definitive experiment using spheres of 4 different materials.
Which ones?
Copper, which is diamagnetic, iron, which is paramagnetic, bismuth, diamagnetic, and hard steel, paramagnetic. He rotated each sphere in the magnetic field and used his high-sensitivity galvanometer to measure the induced electric current.
And if diamagnetism was just a simple reverse polarity, the induced current in the copper and bismuth spheres should have flowed in the opposite direction from the current in the iron and steel spheres.
Exactly. But the result was a fundamental philosophical triumph for unification. All 4 spheres, regardless of their magnetic classification, produced an electric current in the same direction.
The same direction.
He called this a truthful and unvarying indication of polarity. The polarity that was induced by the external magnetic force was identical in all the materials he tested.
So if the underlying polarity is the same, then the repulsion of bismuth can't be due to a simple reversal of poles. It has to be something more complex in the interaction of the field lines.
Precisely. This observation encouraged him to trust the simple, uniform result, the induced current, over the more complex, compound phenomenon of the mechanical repulsion. He concluded that phenomena which appear reversed, like the repulsion of bismuth, must be compound in their nature.
Meaning the effect wasn't the material suddenly becoming a magnet with opposite poles?
No, but rather a subtler effect related to how the material mediates or conducts the field lines passing through it.
This research then culminates in a truly spectacular large-scale hypothesis. Realizing that magnetism affects all matter, including gases, Faraday took this universal classification and he applied it to the biggest system he had available, the Earth's atmosphere.
And this led to his theory of atmospheric magnetism.
It started with a key experimental breakthrough.
Yes, the experimental proof that oxygen is a paramagnetic gas. When he directed a stream of pure oxygen into a strong magnetic field, it was clearly drawn toward the axial line, confirming its weak attraction.
So if oxygen makes up about 1/5 of our atmosphere, why isn't the entire atmosphere visibly magnetic? You'd think we'd notice.
Well, the effect is very subtle. Oxygen seems to have the least diamagnetic force of all the vapors and gases he tested, which positions it right on the boundary between the 2 classes.
Okay.
And furthermore, the atmosphere is a mix of oxygen and nitrogen is essentially neutral or very weakly diamagnetic. So the atmosphere's overall magnetic condition is comparatively low. It's weakly paramagnetic because of the oxygen content.
But this small inherent magnetic nature of oxygen became the central piece of the sun and atmosphere hypothesis, which was intended to explain the mysterious daily fluctuations of the Earth's magnetic field.
Right, and this is where the concepts get truly innovative.
The hypothesis is based on thermal dynamics affecting magnetic susceptibility.
That's the key. The principle he established is that heated air is a worse magnetic conductor than the surrounding cooler air. Since oxygen is paramagnetic, heating it causes its particles to expand and separate, and that reduces its ability to transmit the magnetic lines efficiently.
So as the sun moves across the globe, it heats up a massive parcel of air.
And changes its magnetic properties.
Right.
That mass of heated, expanded air beneath the sun assumes a relative condition of diamagnetic polarity compared to the cooler, better conducting air around it. This large, localized region of poor magnetic conductivity acts as a distortion in the Earth's otherwise uniform magnetic field.
And this is where he introduced that beautiful concept of the magnetic lens.
He argued that this warm, poorly conducting region in the atmosphere acts as a great magnetic lens, able to refract the lines of the Earth's main magnetic force.
So it bends the field lines.
It bends them. Because the heated air resists the passage of force lines more than the cooler air does, the magnetic lines of force will tend to open out or separate and diverge when they pass through that heated region. And this warping effect is transmitted down to the surface, causing the subtle swing we see in compass needles.
That is a complex yet elegant mechanism. It links solar heat, atmospheric composition, and terrestrial physics.
Did he have any contemporary data to back this up?
He did. He used meticulously collected data on the diurnal or daily variations of the magnetic needle. He noted, for example, the mean diurnal variation of declination that was observed in St. Petersburg between 1841 and 1845.
And what did that data show?
The data showed that the variation was strongest in the summer, about 1.52 minutes of arc in June, but it dwindled dramatically to only 0.77 in the winter.
That's a huge difference.
It is. And this seasonal change aligns perfectly with the prediction of the magnetic lens model, where the sun's stronger, more sustained heating during the summer creates a larger, more powerful refracting lens in the atmosphere. And he also found that the timing of these daily swings seemed to depend on geographic location, in a way that wasn't just purely tied to local noon.
That detail really strengthens the atmospheric mechanism. He noted a remarkable difference in the timing of the day changes between observation posts like Hobarton in Tasmania and Toronto. The changes at Toronto occurred about an hour before those at Hobarton.
Which is strange.
It is, because if the daily swing was governed purely by the astronomical meridian local noon, the timing relationship should have been different. And this led him to suggest that the effect relies more on the position of the sun relative to the magnetic meridian. The atmospheric lens theory, where this distortion sweeps across the Earth based on magnetic alignment, successfully explained these subtle geographical timing discrepancies.
Stepping back, the scope of Faraday's work is just astounding. You have the unification of forces, the reality of force fields, a universal material classification system, and a theory of atmospheric geophysics.
It's incredible.
But the foundation for all of it remains his sheer commitment to experimental rigor, which is evident even in his most public, celebrated work.
His legacy is just intrinsically linked to his methodical approach. He never made a claim he hadn't tested exhaustively. And his ability to communicate complex science to the public, like in The Chemical History of a Candle, it just demonstrates his clarity of thought, which mirrors the clarity he demanded in his lab results.
Let's revisit one of his classic public demonstrations.
Yeah.
The one showing the power of water's state changes. The steam container collapse.
Yes. This was a demonstration designed to show the fundamental physical process of condensation. He would heat liquid water until it became steam and then seal the container.
And then?
When he plunged it into a cold bath, the container would suddenly and dramatically collapse inwards.
A very visual effect.
Very. And it demonstrated the immense power of the vacuum that's produced as steam instantly reverts back to a minuscule volume of liquid water. The core concept he emphasized was that the water simply changed its physical state. It didn't disappear. It proved the continuity of matter.
Similarly, his famous candle lectures were rooted in chemical proofs that, while they seem simple to us now, were entirely decisive at the time. He had to prove that combustion produces both water and carbon dioxide.
And he did so masterfully. He showed that water is a product of combustion, specifically the hydrogen in the candle combining with the oxygen in the air.
How did he prove the foggy stuff was water?
He collected the condensate from inside a chimney placed over the flame. His definitive chemical test was adding a piece of potassium metal to the collected substance, which immediately took fire.
And potassium only does that.
It only combusts violently in the presence of water, offering irrefutable proof.
And what about the carbon component? That's equally crucial.
The carbon in the candle combines with oxygen to produce carbon dioxide. He confirmed this by demonstrating that the collected gas turned lime water cloudy, the classic test for CO2. But then, to make the lesson truly relatable, he immediately followed this by showing that human breath does the exact same thing, turning lime water cloudy when exhaled. It's a powerful analogy between the chemical process of burning fuel in a candle and metabolizing food through respiration.
It all comes back to defining phenomena through the action of particles, which he also used to explain the various modes of electrical discharge, the spark, the brush, the glow.
Exactly. Discharge phenomena, whether it's a tiny spark or a continuous glow, they all rely on the same fundamental principle of induction and the action of contiguous particles being pushed past their polarized tension point. Once the tension is too great, the particles break down, discharge occurs, and you get a flow of current.
And this framework helped him resolve a major industrial mystery of the time: the strong negative charge that was generated by high-pressure steam engines and boilers.
This was a fascinating practical application of his theory. In his experiments on steam discharge, he found that the powerful negative charge generated in the boiler was not caused by mere evaporation, as many suspected.
So it wasn't the water turning to steam.
No. Instead, it was caused by the steam passing through the cocks. It was a phenomenon related to friction. Crucially, he discovered that if the steam had to turn a sharp angle inside a cock, it generated a stronger charge than if it just passed through a straight end cock.
So the friction and turbulence were the cause.
That localized friction and physical resistance proved that the electrical excitement originated exactly at the point of mechanical strain, confirming his principle of localized action under stress.
We've traced a remarkable intellectual and experimental arc today. We saw Faraday unify these seemingly disparate electrical forces, quantify the relationship between electricity and matter through electrochemical equivalence, and then make that monumental theoretical leap.
That force exists in the intervening space.
Via physical lines of force. And this ultimately led him to categorize the entire universe into paramagnetic and diamagnetic bodies.
The lasting impact is really the philosophical framework he established. By proving the universal division of matter based on its magnetic response, he gave physics a new vocabulary and a new way to understand material interaction that still powers material science today.
And his insistence on understanding forces through the intervening medium, the space between things.
Verified through meticulous experimentation like the moving wire technique, it just fundamentally changed the direction of physics. It really set the stage for Maxwell's equations decades later.
It's all rooted in the idea that nothing is exempt from the laws of force.
Precisely. And the depth of the experimental record remains just a powerful testament to the value of rigorous quantitative pursuit of knowledge.
So let's leave you with one final thought, tying back to that incredible hypothesis of atmospheric magnetism. If oxygen is indeed magnetic and its susceptibility is altered by temperature, creating a vast invisible magnetic lens high above our heads. Consider this. If the sun warming the air can twist the Earth's magnetic field by a measurable degree, how much are we still underestimating the subtle but powerful interplay between daily atmospheric temperature fluctuations and the silent global dynamics of the electromagnetic forces that govern our planet?
The invisible architecture of the universe, it turns out, is highly sensitive to the warmth of a summer day.